Hey folks, welcome back to my stream. We'll be streaming for more than 2 hours today. The second stream that I'm doing right now. This will involve a couple of meetings. Uh, First will be design and analysis of a fully local personalized text writing assistant, and the second will be from the Starkly Speaking group by Hannah Stark, led by Hannah Stark. Mars FM generative modeling of molecular dynamics via Markov state models. At first, some emails, the VLLMs, phase transformers. Just paid my Airtel bill. This is the NVIDIA RTX Spark Superchip for laptops and desktop PCs. Yeah, so we discussed about this. We watched the whole video live in the morning. 20 ARM CPU cores and 6144 CUDA cores with 128 GB of LPDDR5X RAM and up to 300 GB per second of memory bandwidth. RTX Spark. This is the N1X chips. So this is the new Spark.
we must give you water on the tube because you don't know otherwise.
Right. I'm not sure that
I mean, in fairness, there's no air on the tube, so like.
I see.
There's this tube.
I only know that they always surprise when it's snowing, and I feel like every year it's snowing in the UK, and they are always surprised. It's always an exception, but it's every year, basically.
But it's the case in Germany as well. Like every time when it's snowing, everything stops. No public transport. All the cars driving with 20 kilometers per hour and so on. So.
I see.
Yeah. You guys can just move to South Africa where I was born, and this is not a problem. We never get snow. You always have to go to school.
Great. Okay, it's 5:01, and I believe I can start by introducing the speakers. For everyone else, just a short reminder that we will record the talk. Only the talk, not the Q&A session, which means I would like to ask everyone to stay muted with your camera off during the talk itself. And once you hear that the recording has stopped, then you can also ask questions. In case you just want to not to forget your question, you can also put it on the chat, and then the speaker can read the question and basically address it after the talk. So with that, I suggest, Linara, can you help me admitting people? Thank you. Great. And let me briefly introduce the speakers. I'm super excited to have Andrei and Jen with us today. So what I could find out that Jen did a bachelor in mathematics at California University of Technology. And then she was pretty much in the industry for quite a few years, right?
Yeah.
Also working at Google as a software engineer and at doing internships. So I'm a little bit jealous because I somehow didn't do this. So really cool. And then you started your PhD at ISTA, right? And you finished just a month ago, I learned it. And now you're probably trying to found a startup or...
That's right, yeah.
Yeah, that's great. So great to have you with us and nice to meet you as well. And Andrei, we met actually at CPAL conference and where he was presenting actually a poster on Panda, and I really liked the chat. So Andrei, you were at ISTA, but for an internship, right? And
Correct.
Now you are at Cambridge for your PhD, and you are supervised by Nick Lane. This is also something I learned. I know him, which is super cool. So really nice to have you here. And I suggest I will start the recording. And as usual, everyone, please your camera off and stay muted. And once you hear the sound, and then you can basically start with the presentation.
Perfect. Thank you.
Recording in progress.
Right. I think that's like the start gun for academia. Right. So thank you everyone for joining. And firstly, I think I speak on behalf of both Jen and myself that, Olga and everyone from the LS unit in Graz, thank you for the opportunity to speak at your reading group. I'm personally delighted and humbled for the invitation. So the purpose of today's talk, so hopefully I won't take too much of your time, but I wanted to talk about our work here called Panzer, so design analysis of a fully local personalized text writing assistant. This was work, as mentioned, that I did during my internship at ISTA. But instead of just speaking about the paper itself, I wanted to sort of take a more philosophical approach and actually talk about some of the really important ideas that come out of this single academic work. So the first thing that I want to mention and sort of make the argument for is that we really need personalized LLMs. And there are two axes that we can sort of view this necessity for. So the first is like a very obvious privacy preserving one. And the second one is an efficiency question. And once we've sort of laid down the groundwork for this, I'm going to actually talk about Panzer as a specific use case into this investigation in a specific domain. But then once we've done this, I'm actually going to talk about something that I call the good, bad, and the ugly. And we notice that these sort of personalized text generation is very cool and very useful. But as we point out in our position paper, it is actually the time now to act on the considerable risk that these technologies pose, and they're not trivially solved. So generally, the presentation that I'm going to give today is going to be a merge of these two papers because the ideas are very linked and they influence one another. But before I begin, I just want to say a thank you to all of the collaborators that were involved in this project. So you can see their names here on the papers. I've cut Jen's and Dan's name on the second paper, but they're in the first one as well. And it's just to say that, even though Jen and I are here presenting the paper, it's not our work alone. And all of the work that has been done behind the scenes really make this project possible. So a big thank you to them. Right. So this is generally how I view typical LLM interaction today. So I got Claude to generate this, so thank you, Claude. But how it basically starts off is that you, as your user at your laptop, log in to your favorite LLM provider. So say it's Claude or ChatGPT. You log on and you type a prompt into the chat box and you send your message, and this message then goes into the nether and it hits some server where inference is performed, and the response is sent back to you over the internet. And generally, this is like very, very cool because it's scalable. Lots of individuals and users can access it, and we see this, being very prolific. And it's also quite amenable to a large number of use cases that people want to use LLMs for. So if you want to, say, ask for recommendations of where to go on your next holiday destination, or if you want a quick and easy recipe of banana bread, LLMs are sort of your go-to source. It sort of simplifies a lot of this process that we had where we were searching through lots of pages on Google search, and it gives you something that is quite automatic. But the problem I guess I have with this is that this type of model of interacting through an API is not really sustainable if we want to sort of carry on with this level of LLM usage. And there are three chief reasons I think this is the case. So the first reason is that what happens when you want to process private information? So in the first case where I'm asking to generate a recipe of banana bread, I don't really imagine this is going to be particularly sensitive unless I'm quite interesting in my choice of ingredients. But if I say I want to ask an LLM to process or give me advice on how I should file my taxes, this is going to be much more sensitive and not necessarily something I want to send to an open server. There might be T's and C's that sort of restrict what my information and how this can be used. But at the end of the day, the moment I click enter and this piece of information leaves my internal network, I have no control of how this will be used and whether it will be used for the wrong purpose. So that's the first reason. The second reason is that, these models are very capable, but they don't come without a fixed cost. So you can, of course, pay for a model on a per request basis, or like some of my colleagues, they actually pay for the $200 a month max version of Claude. And in a world where the prices of these models continue increasing, so you have to pay more to get models of better quality, there is going to be some point where the token economics no longer makes sense for the majority of users. So at least personally, I don't think I would be particularly willing to spend $1,000 a month just to access a model that may or may not be correct on a certain use case that I'm having. Now, the final part is, whilst these LLMs are very good and powerful, and it's quite remarkable that they're able to generate coherent text that that's the first thing that they can do. What is a particular gripe of mine is that I often find myself rewriting the output that I get from an LLM. So it's very obvious to tell when a piece of text is LLM generated, and I actually have to go through quite a laborious process of rejigging the content and using synonyms to actually match what I would have said in my own style and language. And there is also a spectrum here that if I'm editing 90% of the output or even more, for example, it doesn't really make much sense in my use case to be using an LLM. So this is sort of the three reasons that we see to be the case here. And as a solution, the most basic way we can address a lot of these things is okay, let's just host our personalized LLMs at home, and it can actually hit all these three qualities if we do it correctly. So what has been solved already? So thankfully, I think it has never been a greater time to actually try adopt this LLM at home usage, because there's been a considerable investment in terms of, both software and hardware efforts, thanks to people building the VLM, Olama, and EXO frameworks. it's really available to you as a user. You can download the software and you can just use it in one shot. And if you do this and you actually invest a slight amount of overhead capital to buy a couple of, say, Mac Minis or Mac Studios, you get this two birds with one stone scenario that, of course, you get privacy off the bat because your content is not leaving your internal network, and this is great. And you also solve this token economic question that the moment you sort of break even of this initial capital investment, you sort of win in this argument, and you no longer have to rely on fluctuating price models or fluctuating availability. You always have something that works. And also with open source models increasing in quality and catching up to those closed source models, this becomes even more compelling as an argument. But the problem of personalization, this is not entirely solved, and it's also a very fuzzy idea in itself, because we don't really know what it means to be personalized as a model, and what we should do to personalize a model. Is it sufficient to add something into the prompt that we send to the model? Is it sufficient to guide it with some markdown files in the context? Or do we need something much more technically involved to produce something that is useful to us as a unique user that it adapts to our style? So this is where Panzer comes in with our great logo. And Panzer itself, in my view, the way I view it, is it has a dual purpose. So the first purpose it has is it has this sort of general market appeal to the user, where we wanted to create a framework for individuals to produce their own custom and style-aligned LLMs on the cheap. So it is as simple as you downloading the GitHub repository, getting access to some GPU. It can even be a Google Colab instance or a Lightning AI notebook, because we've designed it for this purpose, and then running our scripts and producing a model for yourself. So this, in terms of itself, is this sort of framework and product version that we see. But the second question of Panzer is it's more acting as an sort of academic article or an academic piece of writing, where we're trying to find what the continuum, what the limits of style transfer are. So what we want to know is, when does style transfer work, when it doesn't, and what we need to make it work, and how intensive this process needs to be to make something that is of a good quality that users will want. Now, the particular domain in which Panzer rests, even though it's generally applicable to a larger domain set, is it's on email generation. And there are two reasons for this. So the first one is data availability. So ignoring the fact that leak emails exist widely on the dark web, and we could use this, there is a corpus of sort of samples on email generation where we have unique users and their unique email transcripts, such that we can actually create this data set of style-aligned outputs per user, which was sort of needed in our study of Panzer. So that's the first reason. The second reason is that there is a simultaneous relative simplicity and difficulty of the task. So whilst there is prior work doing this style investigation, their generations are generally small. So what they try to do, for example, is email subject line generation. And I mean, of course, this can be stylized to an extent, but the output of a email subject line is relatively concise. It's a couple of words. I'm not going to put the entire subject matter and the content into my subject line. I'm going to use the body for this. So that's the first thing. We want to focus on actual email generation, because it's much more difficult than these shorter prior works. But also, it is relatively simple, because emails themselves, unless you're encoding entire legal documents into them, won't extend more than, say, 2 or 3 paragraphs. And it gives us a very neat testing ground without going into a scenario of, please generate my entire PhD first year report with a model, which, I mean, I would love for that to be the case, but I think it's quite unlikely given this current scenario. But yes, so this is why we focus on email generation. And how we think of Panzer working is that Panzer is basically going to be a model that lives on your local machine here on the left. And through using some sort of local web server, you can feed into it a prompt of an email that you received. So write an email to Jen thanking her for the coffee. Then Panzer will output, "Hi Jane, thanks for the coffee. I really enjoyed it, Joe." And this integrates, say, directly with your Gmail with an extension that you can actually produce outputs to emails with one click. And this is, again, how we've tied the academic investigation and the product into one investigation. So Panzer, beyond being this framework, is actually a very simple procedure, and most of it is sort of encompassed in this single diagram. So to walk you through it, how you start off with is you first gather some sort of user email history that you want to use to specialize the model. So this could be, say, your professional emails if you want this email to be used just for professional academic purposes, for example, or you could use it for your personal emails. It doesn't really matter. But the point is that once you've established all the emails that you want to feed into an LLM, you take this and you give it to an LLM for a process called reverse instructions. So what you're basically asking the LLM to do is, given the email output that was received, can it generate a prompt that would have likely produced that email response? And what basically this does is it creates a data set of all the emails that you had, but in a sort of prompt response format that can be used for fine-tuning. So this is very necessary because we need to have some structure in this fine-tuning, and it can't be autoregressive. What we simultaneously do is we take the initial email history that we had, and using an embedding model, we embed it into a vector database. And this is important, say, in generation, where if we're responding to a very long email chain and we want to use the initial emails as context to guide the generation, we can do so through some vector search. And this is known as, of course, as retrieval augmented generation, but just mapped into this email setting. Now, once we've established all of this, we go through some fine-tuning process. Now, with Panzer, this can be the same LLM that was used to generate the training data set. It doesn't have to be. It can be any model, of course. But you go through some process of fine-tuning. This can be full fine-tuning or something that is parameter efficient, which we'll discuss later. But once you go through this process, you have your Panzer mail model, and now you can use it for all of your generation purposes. You can plug it in with your favorite inference framework like Ollama, say on your Mac, and you can use it. Great. So the point of this is that I mentioned before that we wanted this to be very usable for individuals. And when Panzer was designed, efficiency was really placed as a first-class citizen because we didn't want it to be a case of, oh, you can do all of this personalization, but you need like H100s to train the model to get it done. Because I don't know many people that are willing to fork out, say, 25,000 pounds to buy a single H100. So what we had in mind is to actually focus on these like consumer cards that have, of course, a realistic GPU memory that is have a capped memory footprint that they can have, but it is a much more realistic setting to what individuals might have access to. So you will find these GPUs in gaming laptops, and they're readily available in the consumer market. Or in the case of notebooks online, such as Lightning AI or Google Colab, this is something you can leverage for yourself if you don't have your own GPU locally. Now, the experiments were conducted in two settings. So the first scenario are ones that are inspired by this, hypothetical 24 gigabyte memory overhead. And to enable this, we really focus on PEPT methods with ROSA. And ROSA is a sort of parameter-efficient fine-tuning method developed by collaborators. And we really show that this is able to give you good quality whilst keeping the memory overhead low. And in the second scenario, we push this far lower in that we push the floor to 15 gigabytes. And this is basically using the same PEPT methods with additional quantization tricks on top of it to make sure that the memory footprint is even lower to make it much more accessible. So this is just on a note on the process to actually produce the Panzer models. Now, diving into the experiments, we start with RQ0 because we are computer scientists. But the first thing that I want to note is that generally, any metric for personalization, I think when you start investing your time into this field and studying it, you realize that the metrics themselves are not well defined. And I think this is partly from a historical thing. So I guess in the old days of NLP, pre-transformers, a lot of the tasks that were used to measure success on NLP tasks was machine translation, where you were basically trying to create a one-on-one copy of your reference and target text. Or it was summarization, where you took very long prompts and you were tasked to create something short. Now, in these two instances, we view that the point of this like LLM generation or personalized LLM generation is the exact opposite. Typically, your prompt is going to be much shorter and your email response is going to be much longer. And what we basically see that traditional metrics like BLUE, so coming from the machine translation community, which is like a precision-based n-gram matching score, and Rouge being the recall equivalent, only take you so far in determining like how good your personalization are. So of course, n-gram matching is good to an extent, but they don't allow for a lot of things like personalization or creativity, and they don't really capture the gist of whether you've generated a coherent and a well-personalized output. In our case, we actually found that a good combination comes with BLUE and the MAUVE scores, where MAUVE is a score that maps, basically matches the similarity between two output distributions. And these two metrics work really well for us. And we found that during our experiments, using these two metrics have a high correlation between the quality of the model that the user gave. And it's actually using these two metrics in concert that allows us to develop these models, because of course we can't allow or can't rely on user studies to guide our hyperparameter search. I mean, it would just be very expensive, even though it may be the most optimal thing to do. So this is just a first thing on metrics to keep in mind, and why we report BLUE and MAUVE scores consistently throughout our paper. Now, going into the first point that I want to drive home from the experiments is that prompt engineering itself is really not enough, and we see this throughout our experiments. So observing figure 2 on the left, we see that in the case of having pre-trained models, so no fine-tuning at all, or pre-trained with RAG, so giving it additional context, gives no benefit or marginal benefit to the BLUE score, where MAUVE is basically like not present at all. You have not been able to do any style transfer. And this sort of counteracts these views that, oh, I can just use the API and I can pin all of my style constraints that I need into the prompt, and I'll let the LLM do the work for me. What we see consistently that whether you're using full fine-tuning, ROSA as a PEFT method or LoRa as a PEFT method, this is really what will drive home the performance by increasing both the BLUE score and the MAUVE score simultaneously to give a model, at least in this metric world, that is of a much higher quality. Then complemented with figure 3 on the right, we see that adding additional context either at inference time through RAG or during training with RAF techniques, of course, can give you a slight boost of giving you something that has better context, but it's really this thing that you need to train the model at some point to alter the weights such that it can adapt to your own style. And this is, I guess, the entire crux of everything, of why it is not just as simple as creating a good prompt and then you can go for it. Now, once we've established this, we see that once you've trained the models, observing figure 4 here on the left, the style is actually distinct. So here, what we're comparing is for each user, we're comparing the trained samples that were used to train the model versus the test samples that the model generated, and comparing their MAUVE scores, so basically the output language distributions that they have. And we view consistently that the on-diagonal elements show us that for every user, you're quite accurately adapting to the style. And I mean, in the case of David, the David character in our studies, this was like perfect. And this is at varying degrees for the different users. But what's also encouraging is that the off-diagonals are very different, meaning that if you compare two users that have very different style, this is actually reflected in the models that you're producing. So this is very good from a metric point of view, and it was showing us that this personalization was indeed true. Then going on to figure 5, we actually see that this process is incredibly sample efficient. So viewing the BLUE and MAUVE metrics on the top and bottom respectively, we see that after, say, 75 emails, you completely saturate the growth of the metric, and feeding in more emails and giving more training data doesn't actually help the specialization in any way. So this sort of gives us a case that, okay, great, this personalization is very cool because it is cheap from both a hardware perspective, given that we've set it up with parameter efficient methods and quantization, but we actually don't need a lot of data, and I don't have to accumulate 200,000 unique email samples for myself. I can do it with a couple that I can gather in a very little time on my laptop. So this was really great, and it shows that this personalization is quite efficient and will be effective to give benefit to users. Now, going beyond the machine learning metrics, we actually started conducting a user study to see whether these sort of beliefs in the metrics showing that we've transferred the style effectively translate into something that users would derive benefit from. So the first thing where we wanted to measure this was this user study on usefulness, where we gave users who have trained their own LLMs, so with their own Panzer models, with Rosa fine-tuning, and a Llama model with RAG. And we wanted them to rank the outputs from these models in a domain where it is fixed, so like general open class questions, or their own prompts where the prompts were selected to be very similar to what they themselves would have received or generated as emails. And across the board, looking at the average score, we see that Panzer models consistently help and improve the score over the base LLM. And this is very important, and it shows that even though the style has transferred clearly based on the metrics, these models are actually more useful for the individuals for whom the models were produced. And we generally see that this usefulness can even be more pronounced in regimes where the task is in own, meaning the emails are ones that you will likely reply to or the ones that you have received. Then the second thing we wanted to detect is recognizability, meaning that if you got, say, 4 email samples, one from a Llama model, but of course the person evaluating them doesn't know from whom the samples received. So one was from a Llama model, one was from Jeff, a control user, and then the 2 subjects were individuals acquainted with one another so that you could have this like personal identifiability. And we basically asked them, can you match the generation to the character that would have generated them? And we see that across the board, users are routinely able to identify the prompt or the response correctly to the individual that was generated. So this was more pronounced for Llama, of course, because the LLM generation is very, very, very obvious and had really long prose. And I think this is not a surprise. Then Jeff was the next category over. And then finally, we saw that, of course, this is greatly above random chance for subject 1 and subject 2. But we hypothesized that the reason there was a lot of confusion between these 2 individuals because the 2 individuals knew one another and they were selected in a professional context, meaning they already had a language that was likely revolving around the same diction and the same vocabulary choice. So the distinction was not as obvious had we really separated these 2 individuals. But nevertheless, we see that this recognizability portion is really happening. The final one that we decided to study with users was this question of deception or suspicion, where we asked individuals that given a collection of emails, which of these would you mark as spam or suspicious? Now, we see for genuine emails in the first row, on average, 24% of them were marked as suspicious. And we believe that this is because we primed the individuals to be generally more careful of the responses that they were reading. But the interesting thing is that if you compare the genuine emails to the Panzer L or Panzer S, meaning the size of how many samples were packed into this model, we see that they're very, very close to sort of the same level of genuineness or suspiciousness as a real email produced by the author. And this shows that, of course, this now has a realistic style component that we've matched, but also we've managed to convince users that the Panzer-generated emails, so things that are still LLM generation, that they're human-generated. And we see that this is miles apart from just using a base Llama model where routinely, even greater than random guessing, you were going to flag this response as suspicious. which is, I mean, it's, I think, very close to what we see in the real world when you're reading LLM-generated text. Now, at this point, I actually want to take a step back a bit and say, this reality that I've just presented here, like throughout, like if we pack some of the results together, this is very scary for AI safety. And the reason that this is so is that modern technologies has really unlocked a very potent combination. So if we combine firstly the sample efficiency point, it actually means that I don't need to invest a lot of time into getting data to sort of use this personalization for a nefarious purpose. I can go onto, say, Twitter, scrape a couple of responses for an individual that I want to impersonate, and I'm done, given the fact that I can do this personalization in less than 100 email samples. Of course, the domain differs, but I think the same conclusions would transfer. The second point is that, as we showed here today, that this personalization and inference point of view is really not rocket science anymore. So even the most non-technical individual could follow some to-do document of, downloading the latest fine-tuning framework, fine-tuning a model on some email samples that they've collected, and then they effectively get a personalized model for free. And in a world where we only have good actors, this is fine, right? Because everyone will use this for really good purposes to produce their emails, say. But what does it mean in a world where we have obvious bad actors and who are going to view this technology as an opportunity for exploitation? So the point that we are making, and this is prevalent more in our position paper, is that these efficient and personalized LLMs really exacerbate current attack vectors that we see in AI safety. And what we also make the claim is that this textual domain is perhaps more dangerous than I think what the domains that people associate with AI safety. For example, when I generate an AI video or an AI image, it is more often than not, I'm able to distinguish very quickly that this is in fact AI generated. So we have very famous examples where we have, an additional appendage on a hand, or we have, the Will Smith spaghetti eating meme, which is oftentimes a point of comedy. But text doesn't have this quality. It is just black and white characters on a page. And it's very difficult, unless you infer the style very well, to tell what is fake and what is not, and what is LLM generated and what is real. And we think that the textual domain is really, really having this quality. And the domains in which we see that, we give examples of a couple of these attack vectors, and we really see this causing issues in phishing, for example, where instead of just sending a random email and saying, oh, I'm someone that needs urgent help, please can you wire me $1 billion to this remote offshore account in the Canary Islands, you can actually spend a bit of time as an attacker to create something that is much more human and much more personalized to the individual you're trying to sort of fraud. And I think that the phishing attacks themselves will probably increase in frequency, but that's not the problem. The problem is that they will increase in their success ratio, where this human component, which will actually trigger a person to believing in the phishing attack, will actually will kick off, and we'll see a greater increase. Sort of the flip side is that we can see a very similar thing in character assassination, where individuals can take your email samples online and pretend to masquerade as you and sort of damage your professional reputation, say, if they know that you're employed by a company, for example, Google, and they post really condemning views about the company, even though this is not you doing it. The output is very, very convincing, because your colleagues will say, wow, that style really, really does sound like Andre. Like, this is really bad. The final point that we also mentioned in this position paper was this argument of scholastic dishonesty, where I think using AI in education generally is a pretty good idea because of the personalization, how it can help individuals learn. But there's also this risk where individuals will take LLMs, generate entire outputs of academic assignments, and post it as if they were their own. And now we're currently in a place where this is good because you can feed it into an AI text detector and it will come up true. Or if you spend a bit of time looking at it, you will see that it's LLM generated. But if this personalization gets to a point where it's so well done that it preserves the quality of the output, but completely masks the style, there is almost no hope of sort of detecting these AI-generated tests. This was, of course, in the academic environment, but it could be in other environments, of course. And the reason why we see this being a problem is that this textual domain is not covered by legal frameworks at all. So, for example, in the International AI Safety Report, the textual domain is alluded to, but there is a very, very, very big focus on the video, the audio, and the image element. And this sort of the textual domain is an afterthought, and we think it shouldn't be. And the models themselves really do not safeguard against these sort of qualities. I think many people have managed to go online to their favorite AI provider and perhaps even zero shot, or after a couple of prompt turns, they can really convince their LLM to output something that they shouldn't. And we give a couple of examples of this in the position paper. And now it comes to the question of what should we do to address this? And our position paper makes sort of these points that we should do. So the first thing is that we need more research into model safety. And I think this alignment direction is really good, but we need something that is a lot more robust. So something that I can't just prompt the model a couple of times or prompt it in a specific way and I'll override its safety, or methods that there's been research where you can take a couple of email samples and I can completely destroy the internal alignment of the model while preserving its quality. So the safety, while it should be there, it shouldn't be so easily destroyed. The second point, and I guess this is where Panzer falls in, is that we need to have a better understanding of how feasible and how far LLM text personalization takes us. So of course, this was done on emails, but if we want to truly understand how impactful this needs to be, we need to really branch out into different domains and different use cases to understand how far it goes. Then a third point is that we need to figure out a way of how to sort of attribute and watermark LLM usage, because as was the case with Panzer, this can be typically done in a completely anonymous way. A user can download a model from Hugging Face that is open weights, fine-tune the model, and start performing inference, but we have no way of attributing which LLM outputs belong to each user, nor which type of model they used. Now, it is not entirely clear whether there is a machine learning solution that is machine learning native, or we need other computer science disciplines to interact with the machine learning community to safeguard against this. But it is definitely the case that we need some way of auditing sort of the usage of open source language models. And the final point, I guess, is the least surprising of the four, is that we really want to encourage policymakers and people who have influence in the creation of legal frameworks to put the textual domain along with the other domains of sort of foundation model generation as first-class citizens when talking about these AI safety issues that might come out. Now, just to conclude and wrap up the presentation, even though these risks in text generation generally do exist and we are sort of aware of them, I think this does not trump the point that Panzer itself is a very useful technology. So provided it's used in the correct way, it can provide immense benefit. And I've really noticed this for myself when I was involved in the project and we were testing it. Panzer is readily available, and I've linked the code repository there on GitHub at the top, and also the other two papers that are linked to it. And I really encourage you to use it for yourself. It is very simple to set up, and it takes a bit of time for you to wait to get the model trained. But beyond this, it's not incredibly involved, and it's quite robust given our extensive academic study of the setup. And the second thing is, whilst maybe some individuals in this call aren't people from this domain, I think we need to generally as a community, like the ML community at large, have an increased motivation and urgency into this AI safety research, particularly for the textual domain, because we see that these technologies are really advancing at a rapid rate, and we need to find mechanisms that are robust and that will transfer when personalization is in the question as well. Now, as a final point, I think as was mentioned earlier in the call, Panzer is actually becoming a commercial entity now. And if you have any thoughts, ideas, feedback, or if you actually want to beta test the new products, please let Jen know. So her email is here. And I think this is very good, and I think I speak on behalf of Jen here, where any interaction with the framework is very helpful, because ultimately you want to cater the technology for users that you're creating for. And without this, without further ado, I think this is the end of my presentation. Thank you for your attention, and I'm happy to now open the floor to questions and answer some if people have.
Recording stopped.
Thank you very much. Very inspiring presentation. Are there any questions from the audience? And while everyone else is thinking about their first questions, may I ask one? What I was thinking about is about the following. So I don't know how do other people use emails. I would speak of myself, but emails have a certain depth, right? Like organizational stuff, maybe summaries of some ongoing events, whatsoever. So everything you respond is probably not too deep compared to something like a scientific paper. So what I was wondering is these 100 emails that you need for fine tuning. So if you would kind of compare like Slack messages, emails, and something like scientific papers, do you see any difference? Like you need more papers and fewer Slack messages? Is there any dependency there basically on the task difficulty?
I think this is probably a question of like domain transfer. So in a part of the contributions of Panzer that I didn't mention was that we actually contributed some of our own email samples. And this was because like, even though these email generation sort of benchmarks exist, they're incredibly sparse and they're not that big. And when we were creating these data sets and when we were testing them, these sort of test and train mechanisms were mapped one-to-one. And I think if you try, train your model on just like very short prose and extend them to like commenting on scientific articles, it probably won't match and you won't have the qualities. But another point to mention is that even though this fine-tuning process occurred, the actual benchmark performance of the model that was underneath the hood didn't die. So you were able to preserve this. So of course, you actually change how the model outputs, but the quality and the knowledge that is in the model doesn't change. So I think this is also an important point here.
Can I also jump in a little bit here?
Go for it.
Yeah, so one academic challenge here is that data sets of personalized, writing are already very sparse with very good reason because it's very private data. But cross domain data sets where you sort of combine the same person, different sort of modalities, straight up don't exist. And so it's very difficult to sort of study transfer in that sense. What I can kind of share unofficially from the research work we're doing now is that when you get to sort of greater depth writing, where you sort of tap out first is on a sort of LLM you can run locally, even with quantization. At some point, you need more than whatever it is, 9 billion, maybe like 15 billion parameters, whatever you can fit on a MacBook, say. So you have to, in some way, call out to like a large LLM, or maybe someday something with mixture of experts will be good enough. We'll see. But then you can still personalize what comes out of that, and for that you don't need. You can already do quite good work with a few hundred paragraph length samples.
Thank you so much.
Yeah.
Other questions from the audience?
Hey, so I had a query regarding the fine-tuning via reverse instructions. So you delved upon the full fine-tuning and the two PEF methods, like the robust adaptation and the low rank adaptation. That's the LoRa. And like, I would like to ask, like, whether RAG can bring other kind of improvements like the results that you have had here, or like if we have a larger context length, then if we apply finer benchmarks to use those context properly, so can we kind of uh, do our tasks with fine tuning and we like not require RAG. So like
So we actually studied this at the time we did the Panza paper, which at this point was 2 years ago about. maybe a year and a half.
Mm-hmm.
And at the time, RAG was as simple as, or anything that they called context or whatever name they gave it in different papers was basically just past history, right? Or the most relevant bits of the past history, say like past emails. And we tried actually feeding like all of the emails for a couple of our users to ChatGPT as context. And we still didn't get anything that looked like personalization.
Hmm.
What we did find was that it did boost quality a little bit when also combined with fine tuning.
Mm-hmm.
I think with reasoning models, this has gotten better because we tried it more recently, and what ChatGPT and things like this end up sort of doing is sort of saying like, oh, I see when you write a recommendation letter, maybe like you talk about the person's personal qualities first and then about their professional work or whatever. And so you kind of get a little bit way more structure like this, which is actually very nice.
Hmm.
Um, but I would say it looks like fine tuning is still quite necessary to get a really compelling model.
Yeah, yeah, like we kind of also I personally tried on the podcast. Like we were experimenting since you used a complete end-to-end emails. So we tried our RAG system on podcasts and
Mhm.
like full transcripts and trying to get information out of it and based on the questions of the users like and we like came to the conclusion that at that time this is 3 years back we also came to the conclusion that fine tuning was kind of required but RAG is useful for that kind of context search or just kind
Mhm.
of when you just need some vector database and you put in some documents and you get in information out of those chunks quickly. So like yeah,
Mhm.
that was the use cases that we tried on.
Yeah.
Mhm.
And I want to mention, like, this is an active research area, like, not necessarily just with us, but a lot of people are asking, how do we really capture the information about a person? Like, there's these proposals for sort of memory or associative memory models that sort of supplement,
Hmm. Yeah.
anything that's more like style personalization and so forth.
Yeah.
Like,
Yeah.
it's very cute. Like, there's one paper that sort of like uses an LLM to write like a little quiz about you from reading your documents, and then it trains the
Hmm.
LLM on this quiz.
Yeah. True. Like we were experimenting with graph rags at the time
Mhm.
when Microsoft's that came out that was very popular and a couple of other variants with simple vector databases and we found that like rag was kind of best in case of when we are trying to retrieve those personal
Mhm.
information. So yeah, that's the use case that we tried.
So I'm curious, actually, since this is meant to be a discussion, maybe I can ask a question. Because
Go ahead.
like when you play, so with RAG, like one thing that I kind of found was that well, you can always do the thing where you feed it basically everything you know, but when you actually start pulling from your RAG database, it seems like at the time we were looking at it, the ways to pull were not very sophisticated. It was some sort of cosine similarity or something like this. And this seemed like a huge loss. Like surely there are better ways to pull context. And if anybody like has ideas, thoughts, experiments, feedback on this, I'd be really curious to hear it. Is it still an unsolved problem?
Likely.
I would say generally,
Yeah.
But since you mentioned this, I was also curious. So we treat it as style transfer, right? This personalization.
Mhm.
But you also mentioned that there could be some memorization going on. Also, can you disentangle these two? Is it actually an idea, or is it not necessary? So basically, memorization of the content
Mhm.
versus style transfer. Right? If you do style transfer on the picture, you don't change the picture. You don't change the content. So how does it work with emails?
So did you mean like factual content versus just stylistic elements? Was
Yes,
what you
yes,
meant by
yes, yes.
memorization?
Yeah, yeah, exactly, exactly.
Yeah, so at the time, sorry, Andre, I'm answering all these questions. If you want to jump in, please go ahead. But at the time we did the paper, it wasn't, there weren't very good techniques to sort of measure factual content. So we kind of just said, oh, we're using Blue Score for word retrieval and, things like addresses, whatever are words. So we'll just stick with Blue, which was not my favorite part of the paper, but overall it seemed okay. From human review, like the quality of the outputs. Now there's a lot of LLM as a judge techniques that we're looking at to sort of pull, facts, entities from messages and compare them either against, what you want to be there or sort of like historical information. I don't know how I feel about LLM as a judge. It feels like the sort of thing that could be tremendously biased and you'd never know. But it is very effective for that sort of more open-minded task.
Yeah, yeah. I see. Are there more questions? Doesn't look like, but since everyone is staying in the call, everyone wants to try actually Panza, right? At some point. So all the best with the business model. Thank you so much, yes, for today's presentation, and have a pleasant evening, everyone.
Thank you guys
Thanks
for
a
listening.
lot.
Bye.
Thank
Take care.
you.
Bye.
I guess I'm asking for the group. Francesco, do you know if Hannes is delayed in some way? Maybe send him a text or something.
No, I was wondering the same. I'm actually not sure.
Okay. Do you want to DM him in a couple minutes, maybe, if he's
Yeah, I can drop actually him an email. I don't think
yeah,
I have
whenever
him
you
on
want.
Slack. Yeah.
Yeah, are we waiting for Hannes to join? Because I think like Hannes is in interviews today, so he told me to host the reading group for him.
Yeah, if that's what you heard, that's good to me. Yeah, we can go ahead then. But we didn't get neither me or Casper got informed, so that's why I thought we were waiting for him.
Yeah, I think he's in interview today, so he wouldn't join.
Cool. Shall we start then?
Okay, that makes sense. Yes.
Yeah, I think we can start.
I guess I just want to make sure quickly that the meeting is recorded. Yusin, are you able to record the meeting?
Yeah, I'll record.
Perfect. Thank you so much.
Okay, so I guess you can see the screen, right?
Yeah.
Yeah.
Yeah. We can see the screen. Perfect.
Okay, perfect. So yeah, a bit delayed, so I'll probably keep my part shorter. Yeah, so hello everyone. So today me and Casper will be presenting this work that was accepted clear, I guess 2 months ago or whatever that was. And so the paper is of course available. There will be a link to the code, I think at the end of the presentation. Code is public. I will spend the first part of the talk to give you an introduction to the problem and what people have done in the space. And then Casper will actually talk about the methodologies, what's novel about our approach, and the empirical results. So the first aspect we should probably consider is like, why do we care about molecular dynamics, especially in the context of understanding protein function? I'm not a biologist by in terms of background, so I will try to do my best here. But I guess we are all familiar with recent deep learning approaches to protein structure prediction. I guess one noticeable example would be AlphaFold3. That is a sequence to structure genetic model applied to actually biomolecular complexes besides protein. But in the context of protein structure, as most of the training data in AlphaFold was made of PDB structures, the output of the model often resembles such a structure. And so you kind of have an idealistic understanding of what the protein structure should look like. And in a realistic scenario, proteins are not just crystals. They're not falling into kind of a single static idealized structure, but they keep moving. And it is in the kind of motion of proteins that interesting biology lies, right? And when I'm referring to motion of proteins, I'm not just talking about thermal wiggling. So, because if you kind of like have a protein in solvent environment at room temperature, the protein will keep constantly moving, and this is usually just given by kinetics and of temperature and energy. But what's more interesting for us, especially in the context of like drug discovery, is that a protein can undergo significant changes in its conformation, and these changes are often key to understanding like how a protein function, when it stops functioning as it's meant to be. So, for example, a protein can we know they can be folded, but it can also be misfolded, and this can be driven by sequence perturbation, by environment changes. Active and inactive states are often determined by large domain motions. So you have this like uh, protein that can open up, they can close, they have like this rotation of domains. And perhaps even more interestingly, you have a protein that in apostructure may not look like druggable. So like the surface is like inaccessible for compounds, but then the protein can enter a transient state where it actually becomes druggable. Like a cavity appears at some point and it will disappear very quickly usually. And the key would be to try and target that protein in the transient state where a ligand can bind to it when that cavity is available. So we just mentioned that a protein can be in a multitude of states, and that interesting biology lies in the transition across such states. But the question is not just about identifying what are the states that a protein can take, but more importantly, perhaps what's the likelihood that a protein can take a given state, and what are the possible transitions across one state to another, right? So if we just said that there's like a cavity or a cryptic pocket that can form, what is the likelihood of that occurring? Is there anything that can accelerate or facilitate that formation? And if a protein can misfold in a given environment, what kind of paths it can take to misfolding, and so how likely this will happen. So in the moment we kind of enter the realm of probability, so what's kind of the likelihood of a given state, then we enter the formalism of the Boltzmann distribution. So if you are given a constant volume and temperature, for example, then the 3D conformation of a protein X will be following the Boltzmann distribution. So this is to an extent encoding almost virtually any information that we are interested in from an application perspective about the protein of interest. So if you were able to sample from the Boltzmann distribution directly, then that would be like enough to understand protein's function, to estimate probabilities of events, to quantify thermodynamical functions that are like binding and whatnot. So that's like the absolute goal that we have. But the problem, of course, is like this distribution is not easy to sample directly from. And therefore, one active area of research has been recently, if genetic models have dramatically expanded and accelerated protein structure generation, can we move to the next step, which is besides just static structure, can we use the genetic models to directly sample from a protein's Boltzmann distribution and therefore explore all the many conformations that a protein can take? Now, before we discuss genetic models and deep learning based approaches, we already have a computational engine to produce Boltzmann samples, and that's molecular dynamics, or for short MD. So first of all, what is MD? This is a system of equations where we evolve positions and velocities of each atom following basically Newton's equation. So we have forces, which just minimize an energy, and then you add some other terms, usually some friction, thermal noise, and so you have this kind of like microscopic atomistic movement, as for example in shown below, and you solve this equation and you store frames at a given regular interval, right? And so you have essentially like a video of a protein or a biomolecular complex at full atomistic resolution. So water, hydrogens, everything is in there. Now, arguably the most important aspect of MD is that under general assumptions, MD is ergodic with respect to the Boltzmann distribution, which means if you have a static function that you want to measure, for example, what's the compactness of a protein, or the thermodynamical quantities, like for example, related to the folding free energy. So any kind of free energy difference, which is virtually all the quantities we are interested in drug discovery, whenever there is binding happening, the ergodic property states that the expectation of such a quantity under the Boltzmann distribution can be computed by computing the expectation of the same function over a sufficiently long MD trajectory. So instead of directly sampling from Boltzmann, you solve the MD equations for a long time. You save frames at the regular intervals so that they are decorrelated. And then you can just compute an ensemble average of any quantity of interest over these frames. And this will be approximately equal to the true expectation under the Boltzmann distribution. So this is a very nice property, and one of the main reasons why we are using MD in the first place when during drug discovery campaigns. But the catch is, like, we just said that this simulation has to be long enough, and when you solve molecular dynamics, you usually integrate these equations with very, very tiny step sizes, like order of the 1 to 2 femtoseconds. So you take these very small step sizes, and if you try to increase that, eventually you have compounding error effect, and the equation will basically blow up. So you need to take these femtosecond integration step sizes. But now, how long is long enough? And that's where the kind of like curse of biology arises. So I'm going to give you an extreme example first, and then a more general explanation. In the context of drug discovery, for example, we are very much interested in, for example, the residency time of a drug. So if you have a compound, this compound gets in your body and eventually binds to a target, let's say it's your primary target, then how long does it stay bound to that target? And we have drugs that can safely stay bound to a target for like seconds up to hours. And now if you think about using molecular dynamics, for example, for brute force computation of the residency time of a drug to a protein or to a target, then a second will be 10 to the 12 calls of your molecular dynamic equation at femtosecond resolution. So this is, no matter the GPU prioritization that MD is undergoing, this is unfeasible, and especially to be done at the scale of chemical spaces exploration. So this is an extreme example, but more generally, the reason why biologically relevant phenomena are inaccessible is that the energy landscape induced by the Boltzmann distribution is very rugged. So if you see this diagram here, there's a bunch of different local minima which are separated by high energy barriers. And the higher the barrier, the more time it will take for an MD trajectory to go from one local minimum to the other local minimum. But the problem is precisely in these transitions that interesting things can happen. Like, it may be in one of these transitions that a non-druggable protein actually becomes druggable, for example. And so MD is powerful, but is computationally expensive to the extent that we care about, covering the distribution of and the different conformation that we are interested in. And just to give you more like quantitative measurement of that, if you take a protein that is quite small for our standard, so there's not even 200 residues, even if you don't model water explicitly, so you just have this kind of like classic approximation, then you will only be able to simulate less than 2 microseconds of simulation a day on like, an H100, for example. So the scale of biology is still to an extent inaccessible by brute force MD simulations. I should mention here, out of like scientific rigor, that of course MD is actually an umbrella of tools. What I'm referring to here is classical unbiased molecular dynamics. There is a lot of research on how to bias molecular dynamics to actually accelerate sampling, but this will open a box of that I'm not maybe preparing the scope of this presentation to navigate, because there's a trade-off there. There's other complications that arise on how to decide how to define the bias and so on and so forth. So this was the setup, and then briefly, like what people have been doing in the space to go after this problem and use generative models to accelerate or replace molecular dynamics. So for my a very general recipe, you have your favorite generative AI network. You take as input noise, sequence encoding, because you want a single model trained on multiple proteins. You want this model to generalize across unseen domains. And then you train this model to essentially emulate molecular dynamics, right? Ideally, the output of this model will be samples that are virtually indistinguishable from the frames of your molecular dynamics data distribution. One important catch that nobody truly mentions is like existing works, as well as the work me and Casper are presenting today. We don't really handle the full physics of MD. There's still an approximation here. For example, as I mentioned earlier, molecular dynamics can explicitly account for the contribution of solvent and of hydrogen bonding, but generative models that try to kind of emulate molecular dynamics, including our work, we usually operate on a reduced dimensionality manifold. So for example, we only look at the backbone and torsion angles of the protein. BioEmu, for example, only looks at the backbone of a protein, so it's even further coarse graining, but we don't account for this hydrogen effect and the periodic boundary conditions, the water contribution. So there's still a simplification going on where some of the physics is kind of removed from the framework. And yeah, so the existing approaches, I think this term was introduced in our paper. It doesn't matter, but like we call it MD emulators. The reason being that one of the key objective molecular dynamics is the transition density, p tau. So once you have a lag time tau that you fix, then p tau gives you the likelihood of a given state xt evolving to a conformation y within a lag time tau. So again, in practice, what happens is the integration step size of MD is 1 femtosecond. So let's say the fixed lag time is 1 picosecond, so 1,000 times larger. So this transition density essentially slices the trajectory by a fixed lag time of 100 integration steps, and is giving you a distribution of frames that are separated by this lag time. Now, the class of MD emulators are generative models whose objective is to sample from this transition density. So what's happening in practice is you have your MD trajectory, you slice your trajectory according to your lag time tau, and you train your generative model to transition from one frame to the next frame separated by tau, right? And there's a list here that is absolutely not exhaustive, but there's a lot of works in this space where the objective is the same, but sometimes they change, for example, the flavor of the generative model. Some networks, for example, are equivariant, some networks are not equivariant, but they all try to sample from this transition density. Now, I should probably mention this very quickly. Arguably, I would say the best representative of MD emulators we have out there is MDGen. And the reason why I'm saying that's the best is probably twofold. First, they expand this idea And instead of just sampling from the transition density, they sample from the joint transition density. So basically what's happening is like, given a frame X, instead of learning how to jump once, you learn how to jump K times. So you learn basically this kind of video, if you like, of MD at a resolution tau. So you sample K conformations at the same time. So this effectively increases acceleration, is more parallel in a way. But the other reason why MDGen is also like noticeable work is like most of the previous attempts in this space were focusing on very, very small proteins, like essentially peptides. And MDGen has shown scalability to larger proteins. So what's good about these approaches is like they have shown some chemical transferability. So you have a single model, you evaluate on different proteins, performance is decent, but there's much more that can be done. And I think one of the main contributions of our work is actually trying to be more thorough in the difference between training and test, something like Casper will mention later. And as I mentioned, MD emulators like MDGen were able to scale to proteins of hundreds of residues. So we're not just on the domain of small peptides. And these models are faster than MD, at least 100 times faster at generating decorrelated protein conformations, which is good. But there are challenges and limitations. So arguably the most important one is data imbalance. We just mentioned that MD, as you know, if you have your like MD trajectory in the data distribution, most of the time the trajectory will spend a lot of its time into a local minimum, right? This is because the energy is very rugged. So let's say you have a trajectory and you have, for simplicity, 1,000 frames in that trajectory, right? If you think about what different minima of the energy that trajectory has visited, so for example, what are the different conformations of the protein that are biologically distinct that trajectory has visited, you probably have a handful of that if you're lucky. But the amount of transitions that MD has explored between one state to the other is probably not even in the single digit. We're probably talking about single transitions from state A to state B, because these transitions are extremely rare in MD. So from the point of view of your generative model, the training data is essentially swamped by uneventful, uninteresting transitions inside the same local minimum. So most of your network's capacity is spent on learning things that are not relevant and very easy to learn, which is this protein basically vibrating around its minimum. There is not enough time, not enough capacity spent on learning the actual biological transitions. That's the most important limitation. Then the second one is the choice of the lag time is non-trivial, because you can imagine that if the lag time is too small, then the acceleration your generative model will induce will be limited. But if it's too large, especially for fast folding proteins, you may entirely skip certain transient states, which is of course against our purpose. And then finally, because MD emulators, during inference, you sample autoregressively, this can limit your speed up, and more importantly, it can lead to compounding error. So if you want to sample enough frames, eventually you may deviate from your data manifold and get something that, like, for example, has wrong physics, wrong chirality, and things like that. So I'm gonna finish my part by saying MD is an engine built around time, where we iterate step by step to see how a system basically evolve. But in biology, we are often not interested in time and not interested in like the specific vibration and path that an MD trajectory has taken. We are rather interested in what are the kind of large conformational changes that a given protein has undergone, and what's the likelihood of such a transition happening. So in our work, we try to rethink how we actually approach this problem from a generative model perspective, if we were to build a new generative engine, maybe this should not be built around time and this notion of simulation step, but it should rather be built around capturing these biologically relevant transitions. So I stop here and also stop sharing so that Casper can take on and share the rest of the presentation.
Okay, perfect. Thank you, Francesco, for introducing. And maybe I've seen Max, you raised the hand, so maybe that would be a good time to also ask questions if anyone have.
Yeah, sorry, I didn't see that. Sorry.
So like, yeah, I really appreciate the review, Francesco. And I think you did a really good job explaining some concepts that are like very deeply chemical physical. So good job. But like one question would be, how has the field dealt with there being different ensembles, and like, does anyone ever think about like, let's just do like a deterministic thing and then add noise later, or are they always thinking about, well, we'll just train it to be noisy anyway, and that will define the transition? Because obviously it could be deterministic if you weren't noising. So is there any take on that?
I'm trying to see whether I'm understanding actually your question.
Okay, you could
so
do
you're-
dynamic microcanonical ensemble. You can do it in the canonical ensemble. You can do it in the grand canonical ensemble. I'm asking, have people considered doing different kinds of Boltzmann ensembles? And for example, you could just do it in the microcanonical ensemble and then have like some sort of noise being added later. You could have some sort of thermostat or barostat to control the MD later.
That's a good question. I'm actually not sure if this has been the extent to which this has been addressed, attempted from a machine learning perspective. Yeah, I don't think I know the answer to that. Like, or I could point to any work.
Okay. Yeah. Okay, and then the other aspect is, because I mean you showed the ergodic hypothesis, which is great. Like, you mentioned transient states. I don't know if you meant transition states or transient states. In other words, things that it just crosses over a barrier, or you meant things that it's in very short periods of time. So, for example, a transition state, it's never really there because it's just hopping over a barrier and that's an unstable point, versus something where like there's an apo structure that it's only in for a short period of time. And so with that being said, why don't people just make a model that generates, so you have this MD, you have a lot of MD data. Why not just generate structures sampled from the MD data? Why do you actually need to have time involved? Because all we care about in the end is integrating over the states to get properties. So if you already have the states from the MD, why even generate MD? Because that, I mean, in the end, that's what we want anyway, right? When we run MD, we just want the states. So like, why that?
So to an extent, I agree with your take, and I feel like you should hopefully take this question keep your question in your head, because I feel like the next part of the presentation is exactly going that direction.
Okay.
You will see that time is not entirely forgotten in our approach, but for example, we don't try to emulate MD, we try to emulate the Markov state model you could construct on top of MD.
Okay, sure, right.
But I'm gonna give first a premise, because I want to make sure that this is clear. So I don't have a background in MD, so I'm gonna take this. I'm gonna try to like be very careful about my statement, but we were very much criticized, and I think one review or whatever, and their take was like, time is important, time is essential actually for observables. Now, I do think that
it is for some observables, but this is
exactly. So
complicated.
which is why I want to say that at least on paper, that's why I was careful in the slide when I say static. Like, at least on paper, I think if you want to compute kinetics, maybe
Sure.
there might be value in time, but then we enter a complex rabbit hole of like, you will never use unbiased MD in anyway, because
It's true.
Right.
It's
So
true.
yeah. So I want to say, like, yes, for virtually almost most relevant applications, you're spot on. Like, and that's in a way was one of the motivations for our work, even though maybe this could take a step further. And sorry, Casper, because I think this is an important discussion, so I will also comment on this. There are works like BioImmu from Microsoft. There are works that you look at all the frames generated by MD, you forget time, and you just look at that as a distribution you want to match, right?
Sure, yeah.
But it's very subtle, but the argument that we have is like, and we compare with this works later in our empirical results, but like, even if you discard time, the kind of the data imbalance may still play a role there. Because you're kind of like still overwhelmed by what MD has seen in the way you're storing frames.
Yeah, sure.
So I think like in general, I agree with you. We care about the states and we care about biology. We don't really care about time. It's mostly like an artifact. I just want to be careful that yes, there might be scenarios where time may matter, but that's a difficult niche topic. And B, even if you discard time, you need to be careful on how you do that because you might still keep some of the data imbalance problems from MD.
Okay, cool. And then I'm sure Casper will get to data, but like I'd be really interested to see what you've been training this on, because that's a hard question as well. So, but thank you.
Correct. I think there's another raised hand.
Yeah, so
Yeah.
I have two questions.
Mm-hmm.
So the first question regarding the assumption, constant volume and constant temperature. Is it a reasonable assumption? And my second question is regarding the theory. So MD is backed by ergodicity. I just wonder if GM, like generative model, is backed by anything. Like,
No. I can address the second question. Like, I don't think the generative model is backed by anything. The generative model is backed by, you hope it's sampled from the data distribution well enough that it will generalize and therefore maintain the same assumption, but I don't think this is proven theoretically in any way. Regarding your first question, we can open a bit of a rabbit hole there, so we'll try to keep it brief. In general, that's not a realistic assumption. And I feel like from an experimental perspective, it's actually more natural to keep pressure constant, like atmospheric pressure, for example, temperature, and instead let volume change. But unfortunately, well, for better or worse, from a generative model perspective, it doesn't matter because unfortunately, all of these approaches, we're not accounting for changes in volume or pressure because we're not accounting for periodic boundary conditions. We're not accounting for water. That's part of like the degrees of freedom that I mentioned earlier, where that generative models let go and just look at like a protein heavy atom or even backbone representation. So yeah, that would be my answer.
So to sum up, you're saying the assumption is not reasonable.
It depends on your application. What I meant is, if you're saying that was not an assumption, like if you want, you can replace it with pressure and constant pressure and temperature. It's the same thing. Like you can have
depends on what you trained on, right? So for instance, if you trained on like a canonical or a Gibbs ensemble, like the data you generate, the trajectories you generate are going to be likewise. I mean, right? So it's that
exactly. Simple. But from a generative model perspective, it doesn't matter, right? Because unfortunately, your model is still discarding. You're not looking at the box, for example. You're not looking at how that changes in the simulation. So.
Okay. Yeah. Thank you.
Yeah.
I had a quick query here with respect to the MSM emulators. They learn state-to-state transitions rather than learning frame to frame. So, is there a certain advantage on that?
Can I not? We should probably wait for Casper to present his part.
Okay.
Yeah, this is what the second part will answer.
Okay, sure.
Yeah.
Thanks.
Byron, if it's quick, we can take your question and then probably let Casper also start his part.
Oh, yes. Can you hear me okay?
Yeah.
I think so, yeah.
Yes. Thank you. The quick question is like, I'm looking at like proteomic data sets, and basically what I've learned is like unbiased data sets are like around proteomics and stuff like that is probably something I'm looking for, and I can't find a good resource because I think molecular structural dynamics is what like the unbiased is, and then we bend them into like classifications of like different types of like RNA, DNA, protein, peptides, small molecules, etc., versus trying to define it based on protein sequence and other things. Can I find molecular dynamics that are similar in nature across all biological molecules rather than bend them into defined categories? So, are there any good like resources for that, where the unbiased data sets are from humans or whatever, that just looks like molecular signatures without biasness, I guess, or like, do you get my question? I guess it's kind of all over the place. I'm sorry, I'm nervous.
No, it's good. I mean, like, if anyone in this call has an answer, please share in the chat. I feel like the data set we use that Casper will present later is probably one of the best we could find for the reason, like in terms of chemical diversity and structural diversity, as we discuss later. But this is one of the pain point of these methods in general. Like unfortunately, there's a cost in generating MD, and I think Microsoft released some of the MD trajectories they use for BioEmo. But in general, like it's very hard to find public MD data because these are expensive to generate, and oftentimes if they involve proprietary targets, for example, and so people are not that willing to share their dynamics. So you can see what we use in our work, but I don't have unfortunately, I don't think that there's an easy answer for that.
Is there anyone working on this type of creating these, or new hardware engineering or whatever? Any companies or universities?
When you mean this, you mean like the open
unbiased
source in data?
Yeah. Molecular dynamics and structures.
I mean, in the context of proteins, only the biggest releases that I can think of recently were the one we used from the MDCAT from the Fabritis group, and then there were like BioEmo that I know that they released last summer their MD trajectory. So probably from the top of my head, when it comes to just proteins, then the moment you enter complexes, protein ligand, that's a pain because most of the trajectories are extremely short. And yeah, I'll stop here. I've had like bad experiences so far sometimes, so I don't want to like.
All right, that was not a quick question. It looks like so we can move on, or I can email you later. Appreciate it.
Yeah. But please, if anyone has comments in the chat for like, but I think Casper, you can probably start.
Okay, amazing. Thank you again for the questions and Francesco for introducing the first part and motivation. So basically now I will walk over like what we propose as an alternative to MDMUS to overcome all those shortcomings and the fact that we rely on like this explicit time in MD in MD data. So just to start as a concept, I will introduce what Markov states are, because it's like a building principle of what we actually have used in our model, in our proposed generative model. So this is a tool that we sort of want to get rid of this bias of like seeing a lot of high frequency noise and oscillation around the modes in the MD data, because this is in general like it's a very bad like it's not ideal signal for training when training models are seeing a lot of high frequency oscillations around mode, because they tend to just like expectation of something like that it's zero, and it's like definitely confuses models. So we were like, oh, what we can use instead of relying this like fixed lag time that either is too long and then like overshoots, or is too short and mainly sees the high frequency data. So as an answer, we used Markov state models. So I will quickly go through how what is Markov state model and how is it built. So first of all, we project like our MD data onto like some low dimensional space. That could be like we can use TCA, VampNet, or maybe some collective variables like radius of gyration, secondary structures. Then we use a clustering algorithm to cluster within this space our frames, so that we end up with a number like m number of states and the transition between them, and then based on that, given certain lag time, we can calculate the transition probabilities from state to state. As I've like, this is one of the examples that we basically projected our data into secondary structure fraction and radius of gyration, and then clustered. We have 5 clusters, and the transition between them, what is the probability at given lag time to transfer from one state to the other. Yeah, and given that, however, the MSM itself, Markov state models, are not a generative model. It's just a tool that creates a transition matrix and then creates a like fine granularity that we can isolate more low frequency, more significant transitions in MD data from this high frequency transitions that are mainly oscillations around certain mode. And because of that, we introduced this class of Markov state model emulators that are indeed using the MSMs to and port it into like a generative framework. This is also valuable from the point of view that it doesn't necessarily has to be only used as only on its own Markov state model emulator, but it could probably also provide a nice beginning states for like MD, like more sophisticated models to find a few low frequency, like bigger transition, few modes, or like folded state, misfolded and unfolded, and starts the emulation from there. So yeah, our work focuses on introducing this class of Markov state emulators, and particular instantiation that we have. And here I will outline a few, like why this is important, we believe, and why this is overcoming a lot of shortcomings of the all and numerous works that we have seen previously, as Francesco presented. So first of all, the training diversity, because we now operate over the state itself. We no longer rely on the fixed time lag time, and we can see any conformation from given state transforming into any conformation of the other state, which gives us training diversity in the data and the input to the model. And similarly, very often we see that MD data have numerous, like for instance, like numerous instantiation running in parallel, so that we can, and they are separate and non-continuous, and MDMs cannot use them, while MSMs, because we operate over all replicas, the MSMs can aggregate them together and put conformations from different replicas that were not together into same state, and that also contributes to the training diversity. Secondly, this focus on macroscopic transitions, we observed empirically that it contributes to generalization, and it's better signal for the model, because again, we are seeing significant transitions more often rather than just these oscillations around mode, which most of the training time will be spent basically on collapsing to mode 0. This is the advantage of MSM, that we will no longer have that noisy input to the model. And lastly, because of because of the fact that we operate over states, we can from the same 3D structure, we can generate multiple different conformations that could possibly explore multiple different states, and that would be also generated in parallel because we're using same underlying generative model, and we no longer rely on this sequential generation that MDMs do for learning and for actually sampling. And that also improves because we usually, as Francesca explained, there's this compounding error that NDMs have. So we no longer have to rely on the output of our own model to generate a new sample. And this is more generally like I phrase this as a framework, more like conceptually. And now I'll present particular instantiations of our framework, and then like particular empirical results and experiments that we conducted. So we used the particular instantiation, we called it a Markov space flow matching. Short, it is MarsFM. And it is a model that is using flow matching to do that. But again, I think it's important distinction. While MSM itself is in this clustered and projected on the lower space, we do not rely on this lower space. This is only used for the later stages, as we will see during training. We still can operate on any representations we would like to, basically, and it's only dependent on generative model because we have associated now. The MSM gave us information which basically groups the given frame into given states, but we're still using the given frame and all the 3D representation to train the generative model. So what we've used particularly is we used AlphaFold 2-like and MDGen-like representation when we use like the residue level geometric representation when we have quaternions and rotations that are corresponding to backbone atoms and in given residue, and how they transform from frame to frame. And we also have, and this would be like, it's a four features for quaternions, 3 features for translation. And then we also have the torsion angles, which cosine and sine features that together there will be like 14 features for all of that. Similarly to MDGen, and AlphaFold 2, we use invariant point attention and the IT style transformer to train the flow matching underlying model. Yeah. So just as a simple recap, we use standard flow matching. We define a conditional probability path from a noise to a target sample, and we train a neural vector field to match the corresponding velocity. And then we sample by integrating this learned vector field from noise to data. Very simple, standard stuff. And finally, here is the main novelty and what we actually stand out from previous work, like MDGen and AlphaFold 2, because we borrowed a lot of things from that and from the flow matching itself, is what is actually the training objective and how we form training samples. So in particularly in all the MDMs, we have a fixed lag time. So at the input, we see we see a sample, given sample, and the output we see a sample plus some lag time, right? But we no longer wanted to get rid of that. And here I will outline how we use the Markov state models exactly to get rid of that. So we have pre-computed offline MSM for each protein so that we end up with, for instance, 3 states as on the example. And during training, we sample uniformly one of the states. We take also from that state, we sample any frame, and this will constitute our like x0, like the starting source frame. And then we follow, because we know to which state it belongs, we follow the transition matrix, and with respect to this underlying probability of the Markov state model, we sample the target state, and from this target state we are getting a target sample. And this is basically our input-output situation that we have. Then we use classical flow matching when the input, like the source target, is the conditioning frame, and the output is the target frame, and then we interpolate from noise to target frame, and this constitute our training paradigm. Most importantly, I think many questions are regarding DAO. Again, we use this only to sample training. The MSM is only used to sample these training pairs. And because of that, we do not need this at inference. We hope, basically, and as we will see empirically, that the model itself will implicitly learn this underlying Markov state model for new protein and for the proteins that we actually train over. So yes, and that is the main framework, how it works in practice. How do we sample? So again, no MSM at inference. We don't need that information. So we only need this one starting 3D structure and a sequence, because this is in IPA we use this as the input. And we develop 2 ways of sampling. The first one is only using our model, which is only using MarsFM, and is sampling in a way that we have a starting 3D conformation, and then from it we sample, for instance, 5 new conformations, and then recursively we build a tree that from each new conformation we can sample again 5 new until we reach number of conformations we were targeting. And this is the second approach we will present, is the hybrid sampling, where we combine our method, MarsFM, with the MDGen model, and this is more like a proxy for a proof of concept that our model can be used to first to spawn a lot of conformation in different modes, in different metastable states, and from it we have a model that is more refined on like lower lag time, and it's generating a higher quality fidelity within the region. Yeah. So the last question to answer from our like training schema is, how do we construct Markov state models? And again, the Markov state models are generated per protein once, only for the training set before entire training begins. We define lag time and number of states. Lag time is for the transition probability matrix. Number of states we are targeting, and then this is all global settings that are just used pre-computed offline once. And we did some ablations over, and it's not necessarily the parameters that are massively impacting the performance. So it's like pretty prone to that. For tetrapeptides, we simply build like a Tika plots and then like TICA clustering and it like deduce MSN states from that. And for MDCAF, because those are two data sets that we performed experiments over. For MDCAF, which is bigger data sets, we clustered the states based on the radius of gyration and the secondary structure fractions. And given that methodology, now I'll present our results. So I will focus like I showed an example that for tetrapeptides we use TICA, but this is like a very toy example. So I will only focus now on the big MDCAF data set, which is also, I think, is answering a few questions from before. So we wanted a data set that will cover, there will be some important events that we can observe within the time frame that MD rollouts are happening, so that it's not just a little motions, because basically our method has been developed mainly for that. We don't want to observe just a model that outputs a little wiggly movements around the modes. We want something that can actually approximate those bigger moves. So that's why we found, like, I believe that this is like at the time was the most diverse data set, containing above 5,000 domains. The residues are from 100 to even 500 residue proteins, so like significant, quite large proteins in general. And the data set has 5 replicas and 5 temperatures. We focused our main evaluation on 450 kelvins, since we could observe more transitions, the most significant transitions within this data set than at the lower temperature, because obviously within lower temperatures we have lower movement and lower motions within the same time span. We then evaluated carbon alpha pairwise RMSD to like approximate whether our model, comparing to previous method, can generate the same structural diversity. We also measured with RMSF the per atom flexibility. We have radius of gyration and compare the distributions of generated radius of gyration with Jensen-Shannon divergence and the one that is in MD data. We did same with secondary structure fractions, and finally we also measured the error like in estimated folding free energy that would be estimated from the MD data directly, or the one on the data that has been generated with our model. Most importantly, we follow quite strict train test val split, because all the test proteins have less than 20% sequence similarity to training. And we have around 400, we have exactly 496 such test domains. So they're like in terms of sequence similarity, they are significantly different than what we have seen in training, and this is basically to assess the generalization, because as we saw even within modern folding models and everything, it's the less similar we are, the worse performance there is of the model. So, and yeah, we noticed that from the results we improved upon previous like approaches like MDGen, which is the representative framework we believe and the best performing framework for the MD-EMUs. We also significantly outperform the BioEMU, which is just training entire Boltzmann Boltzmann distribution at once. And we also try to ablate like whether this is mainly an impact of the like many rollouts that MDGen, for instance, MDGen has. That's why we also run multiple MD-gens generated from the ground truth structure and compare against that. Also, like whether it's overfitting to given lag time, and as presented in the results, we are better than all of the combinations. So yeah, from our conclusions and we get the best approximation of distribution of duration radius of the secondary structures and of like protein flexibility. And same with the estimation of folding free energy from the generated samples. And this is more of an illustration how, again, sequentially MD-Gen would generate things at the beginning that are very similar to what the starting frame is, while we immediately go into the regions that are more exploratory or more interesting. We going faster into something that is just differs from the starting frame. And similarly to our MD Amos, we do provide a massive speed up in comparison to MD itself. So we got nearly 3 orders of a magnitude faster than implicit solvent MD, which is like the fastest on AG100 fastest MD simulation that there is. And we can generate around 500 structures of a 160 residue protein within only 30 seconds. So yeah, future work could involve going beyond just MD-CAF, extending it to sequence to structure. Although I believe it's quite easy extension, as we simply take current state-of-the-art models like AlphaFold 3 or Boltz 2, and we train on their output, and we just can combine those two models based on that, because again, we only depend during test, we only depend on the 3D starting structure and the sequence itself. And instead of doing the proxy, like actually using the MD to fully showcase the potential of our method. And that would be all. Thank you. And if there are any questions, I believe we are happy to answer them now.
I guess I could start by asking the from a practitioner's point of view, what was the GPUs and the hardware that you trained on? And
All the models, we just used a single H100 to train them. Although we could obviously speed up to training way more. It was like a few days on single H100, and then the sampling itself is as presented here.
oh, cool.
Yeah, so it's also on single H100.
Mm-hmm.
Perfect. Byron, you also have a question?
Yes, thank you for your talk. It's good that you're on this slide. This 500 structures in 30 seconds, AlphaFold has really helped with protein structure, especially 3D structure, but not in the intrinsically disordered space around proteins and regions. How does this fill in the gaps for AlphaFold and is it ESFold, these open source versus proprietary, regarding like how to actually view a over time?
Maybe it's not my domain of expertise, but in general, I think what is important here to note is that we only train in this CAF domain, and we only train. We do see a 3D input structure. Our model has access to that, so it no longer has all the need to train like AlphaFold to train the trunk, for instance. And it no longer has a need to be diverse in that sense. So we provide physical information through this 3D structure, and I think we believe that that is something that is no longer like it doesn't necessarily require that much of a data generalization to like a lot of the data that they are using. But I'm not sure if I understood the question correctly. So
I guess
yeah.
the other thing I've been having problems with, like, how do you test some of these things in vitro, in vivo, to make sure that, like, because this is like perfect for like drug design and discovery and stuff like that, and therapeutics, but like what would be a next step for y'all if y'all wanted to go to like the wet lab? Like, is this even on your radar, or is that completely, how far downstream from that is this?
I could probably step in, but I think like in general, yeah, this unfortunately there's a few things I cannot disclose, but this was like a proof of concept that Casper and I mostly worked on like last year. I think like in at Valence we are working in this space actually from many angles, and MD is an important piece of the puzzle for us. So hopefully we'll be able to share something that is more is closer to the pipeline. But I think I can't share much, unfortunately. But I think like it suffices to say that, you know, in the context of this work, we wanted to test the idea of being able to sample larger conformational changes, right? And to do that in the public domain, we had to go to like high temperature simulations because that's where it was kind of the best benchmark we could find. From there to be able to say, hey, our Jetty model is actually like able to detect, I don't know, cryptic pocket. This is a long shot. Like we're not there, like for sure. So we're not claiming that. And that there's a challenge there in terms of data primarily. So yeah.
Thank you, I appreciate it.
Yeah.
Hey,
Okay.
I would like to ask about the sampling scheme in the flow matching that you have used here, the tree sampling specifically. Uh, like
Yeah.
you first kind of generate n frames in parallel, and then from that the probability of the generated frame, you generate each frame in series, like so. Uh, this kind of tree sampling, like I was trying to understand what was the metrics like that you used to come up to this particular sampling strategy here.
Uh, I think the main, so we wanted to do something in between, right? Because
Uh-huh.
if we generate just from the starting frame, the starting frame has an implicit bias of transitions itself, so it would actually not approximate fully the underlying distribution or the distribution that we have seen in the data.
Mm-hmm.
But on the other hand, we have, as something both me and Francesco have mentioned, the MDGen and any other model that there is out there suffers from the rollout error, meaning that like if we start calling a model 500 times, and the 500th time we've called it, it relies on 499th generation. And just the model, the output and the quality of the output deteriorates itself with this rollout error. So
Mm-hmm.
we basically, why the tree sampling is meant to be something in between that. For instance, to generate 500 frames. For instance, if we start with like number of children being 100. We have a first frame, we have 100 children, and then it's enough that from the following 3 children, each of them will generate like 100 new samples, and we already got only within two, like only relying on the first output of the model, we are able to generate something that approximates the underlying MSM distribution better and underlying basically Boltzmann distribution better than if you would just call it from the first sample without using 499 calls, autoregressive calls to the model.
Okay, cool. Like, do you have an idea of the complexity, or have you calculated it, like, for the different sampling strategies here?
So technically, it's more like it's yeah. So like just if you look at the MDGen itself, you generate maybe 100 things at once. So that's why their time is quite good. But you generate 100 frames at time, and then you need to wait and take the last thing at the output for the new call. You can't generate them from the same starting frame. But if what we aiming with like this Mars approach is that if the more GPUs you have, the more, because we still interpolate between there's a stochasticity in that, and we from single frame we are able to generate many different modes and many different new conformations. That yeah, we are no longer limited like MDGen and MDMUs by sequentiality of it, and we can do a lot of things in parallel. So it's less about it's also the curse of MD itself, right? Like because it's this extremely small lag that you have to use, and you have to wait basically many days, weeks to actually generate it.
So like the hybrid strategies happens like totally on the GPUs, or is that a combination of CPUs and GPUs that you have?
So I mean, both models can be preloaded, right? So you can they are not that massive in general, like on a GPU. So it can just take directly the output and call the next model.
Oh, okay, cool. Thanks.
No problem.
Hello. So I would like to ask a question. So compared to MD, like the benefit of GM is in terms of computing time. And do you see any other benefits?
With comparison to MD itself?
Yes.
I mean, in general, like MD is supposed to be like in all of this training, it's supposed to be a ground truth. So I believe it is still a bit of a limiting factor that this is our training set, right? So I like apart the fact that we can generate so much, and it also generalizes to new proteins, new conformation. I think this is the main advantage, because that basically means that if we train on much more data, and this, as our proof of concept generalizes well, that means we can like 600 times speed up is basically night and day difference. So but if maybe Francesco, if you have anything to add apart from that,
No, I mean, like in general, the other two improvements you can have with the Spectrum D is one is what Casper mentioned, like as future work, like, and D still requires an input structure, right? And prepare the input structure in the kind of like I say simulation box before you run the simulation. So if your generative model was able to even skip the input structure entirely, this would also like it would be better than MD because you don't need to prepare the structure first before running MD. And then the second axis that you can improve upon, but that's outside the scope of this work just because of training data, is like if you think of MD as a video, right, you can have different resolutions for this video. And resolutions in MD are basically the accuracy of the force field. And now this is outside this work, but you can think of, well, what if now you have a certain resolution during training? Can I train a model to increase the resolution as well? Not just accelerate the video, but just have a better definition. But that's something that we couldn't do, or like we didn't do, just because our training data doesn't have, it just has a single resolution. So that's what the Jetty model has seen, and that's where the accuracy would have.
You see. So, well, can I ask a follow-up question?
Yeah.
So I know, so in the field of MD, I know the Anton and folding at home is very like, I think it's kind of famous for like speeding up MD.
Yep.
And is it like, do you see like the work is different from them? Anton, I know is in hardware, but it's also the purpose is speeding up MD, and
Yeah.
folding at home is also.
No, I think that's a very good question. Like, to an extent, it is true that you could have. I think, like, okay, I want to give you two answers here. So the first one is more like long-term strategy. So it is true that arguably for decades, like that supercomputer capabilities, maybe still to this day, give them an edge by allowing them to run MD at like ridiculous pace. But that, if we look like historically, they're kind of like betting on a specific custom hardware for like, you know, something like MD simulation eventually will not pay off, because you can imagine that the improvements we have on the Jetty model on the GPU side will kind of like compound in the future and eventually allow that to be more possible. Yeah, so that would be one side of the equation. So, but you're right in a sense, like you could take a completely different approach and just go like, I'm gonna build and finance my own supercomputer and run simulation faster. But the other problem is a bit more conceptual, like, and to an extent, we're not tackling that specifically here, which is even with the best supercomputers, certain biological events truly are inaccessible at scale. Like if you want to like brute force compute the residency time of any possible compound you are interested in your design cycle with any target of
So
interest, that
this
will
is
not
the
be
thing that I was
feasible,
talking
even with a
about, the Worklog
supercomputer.
time in seconds
So
for
then at that
those
point,
number of
you need to
trajectories.
think of how to bypass the problem even within MD. So there is a research risk involved. You have to develop
But
a new
they haven't
biased
given
MD,
me
and
the kind of
then
complexity
MD
here.
itself is very sensitive to the input structure. For
Both the
protein, maybe it's
memory
not that
as well
hard,
as
but
the
the moment you
time
start having complexes,
complexity. The
that's a
time
whole
is good,
different question.
but
And
I
so,
was looking at the
yeah, I think like
space and time complexity
Platinum
here,
Jetty models eventually is like, we are not showing this
such that
here.
from a
Here we're
computer
focusing on
scientist
speed. That's
point of
true.
view, I can
But
get
that's
a
kind of like the trajectory is like how you
view
can
of
eventually
how much time
address all
will I
other
require
limitations of
to
MD
run
and
this algorithm,
essentially have a completely different engine that doesn't rely
and
on time, doesn't rely too
can
much on
it
high
be
quality input
improved
structure preparation, and it can sample more faster and
on
better, basically.
100 and
But we're not there
200
yet.
with
This is like
AMD
something
Gen?
that we need to build step by step.
Yeah, thank you.
Yeah.
I mean, do you feel like the field needs like another large open source MD data package? Not to say that like, you know, larger companies like Recursion, which I guess you guys are owned by them at this point.
Yeah.
Or I don't know, say pick your big pharma of choice, right? Or even startup that is doing stuff like this, right? Which there are plenty that are. Is the field ripe for like another MD cath that just better or bigger, or what are your thoughts on that?
I mean, like my thoughts on that is like, sure,
sure, I guess?
if the, it's a bit bittersweet. Like if we looked at like major success of machine learning is, I think the bitter lesson usually is like, it's never really about the model. It's more about
Yeah.
having enough data for the right problem. And but then when you think about like AlphaFold 3 and open and closed source versions of it, to an extent they maxed out anything that is possible. Like and
Totally.
even that even if even considering that the scale of data is still ridiculously small compared to vision and language. So that the honest answer would be yes. We would be doing much well if anyone open source their own data of any modality. The harsh truth is like even at Billions of Recursion, like I think we're trying to be as good as possible when it comes to open sourcing models, like Mars FM last year, the partnership with Balls. This year, hopefully, we'll continue that trajectory. Stay tuned. But then data is always tricky. Data, we always have like lawyers stepping in and say, "Hey, what are you doing with this data? This cannot live." And unfortunately, like it's to an extent, this the scenario where we operate, which is why like even Microsoft. It's very good that they eventually release that data, but that data is not really sensitive. Like protein moving, cath domain, protein moving, this is not really like sensitive. For competences is different, unfortunately. So yeah, it's a harsh truth, but like hopefully we'll find a way of like generating this data and open source it, but it's gonna be a bit tricky.
Yeah, and the bigger problem actually in general is that I don't actually feel like MD is a solved problem personally. Like I think MD itself is
I
still
agree with you.
And so we're not like putting the cart before the horse, but it's like we're not like putting the horse before the cart. Yeah, the cart before the horse. We're not mixing it up quite that bad, but at the same time, it's like, yeah, how do you efficiently sample an intrinsically distorted protein? And the answer is like, well, there's a couple methods that do well for this, but we really don't know. And there's some experimental methods to determine whether the MD is correct, but you don't have anything like a crystal structure, right? Like a crystal structure is a crystal structure. But if you have a bunch of dynamics, it's like to what extent can you really confirm that? So, but yeah, Francisco, I really appreciate the discussion, and Casper, I appreciate your explanation of the model. So beautiful work.
I have a question. Sorry. On piggybacking on that, the crystal structures is like just very ordered proteins, but I've been looking at this protein like Titan on something like that level, that size in the human body. What possible like way could we even start to model something like that? If that's even like
I'm not sure I got your question.
The dynamics, Byron, or do you mean like just
like the dynamics of it, right?
Of like Titan, you're saying?
Titan? I call it Titan because it's so large.
Whatever. Yeah. But you're saying like how would you even do MD on something that's like 8,000 residues long or something?
Yeah.
You would coarse grain everything. You would just make every single amino acid a giant bead, just bounce it around.
Yeah, and you would model that with like H100s and like models and stuff like that, and H200s.
I mean, 10 years ago, I'm sure people did it on whatever hardware they had available. So,
but I think that's besides the point, though, because it's like I just want to touch base on, and I guess that maybe in the interest of time we can wrap up, but like I want to touch base on like the Mark's final point, because if you have to leave with one take-home message besides our work, maybe that I would like all of you to take his point, because I guess from an ML perspective, and people like Casper and myself come from that background, it's very easy to kind of present MD as a solved problem and say, now let's accelerate. But as I mentioned resolution before, like the choice of like force field matter, and when you yes, you can coarse grain system, but then which force field you use for that coarse grain system, that's fully research question. Like this is far from being solved even at the MD level, and even that's why I didn't open, like I mentioned, the Pandora box before, but that's a conversation that I'm not the expert of, but it's very, very long. But MD itself has ways of sampling in a biased manner and kind of like crossing these barriers more efficiently. But then you ask different MD people, and they have extremely different overviews on what's the right kind of enhanced molecular dynamics that you should use, and it's very system dependent. It's if you think about it, like 20 years ago, there was no like prioritization of GPUs, and MD to an extent is benefiting from that as well. So there's more research going on at the MD level just because certain things now are cheaper, more possible to explore. So the extent to which actually MD works is actually a question mark and we're kind of like operating on already at the frontier of what we know and understand. So yeah, so I think it's a good place to wrap up and say we're just tackling the speed aspect of unbiased MD. There's far more work to be done. There's different axes like resolution that we can address, and yeah. So thanks for joining in. I think it was a bit bumpy because of we started a bit late and whatever. We didn't have moderation, but again, code is public and Valence is also actually hiring. So if you're interested in working in this space, please either reach out to me or consider applying. There's like a career page on our webpage. All right, thanks, Casper. And
Thank you.
thanks to all of you. All right.
Uh, Thanks, folks. That was all from today's stream. Got to have my dinner, and let's check on the free account if I have the daily 10 quota. Mm. Oh, used all. No worries. We can take a look at this tomorrow. In tomorrow's stream, we will be going through the remaining videos of Google I/O, analyzing them, and then going through some of the SVCs, and we'll see how Vinicius Jr. performs on this Evo that I have done on him. Right now, he looks good. Let's see. After the couple of more steps, when he reaches his complete statistics upgrade, how well he performs in my team. So yeah, we'll keep you guys updated. Until then, ciao and take care. Bye.